We'll start off today, so we're finishing up, or I guess continuing on with our discussion of circuits. And so there's a couple more, we're going to introduce rules of circuits as we go along that can help us interpret circuits. So we're going to do sort of a lot of trying to interpret circuits conceptually and in words, and then some interpreting circuits with equations and such. And so we're going to hopefully try to connect these. And so this is our next rule. So there's two big rules by this guy here, Kirchhoff, that are super helpful in solving circuits. And so the first one here is the junction rule. And I think about this one kind of like highways. All right? And so this says that the current going into a junction will equal the currents leaving the junction. And so you can write it this way here. The total currents going in equals the total currents going out. Okay, and so that would be looking like this. And so sort of like if there's 10 cars coming this way, and 5 go this way, that means 5 are going this way. So the current coming in will always be consistent at any kind of a junction, and that'll be super useful to us. So someone asked, I don't understand Kirchhoff's junction law. Isn't the current at any point on a wire the same? So we tried to be clear when we talked about this. The current in any continuous piece of wire is the same, all right? But anytime the wire splits up or makes a junction, then the current is going to change, all right? The current it most likely will change in those situations, okay? And so let's go back now to where we picked up. So we talked about series resistors. Let's do a question here about parallel resistors. So a light bulb is connected to a battery. Here's a light bulb, and then we connect another light bulb in parallel, right? What is our parallel rules? Well, if you remember from capacitors, parallel means I can go from like the bottom of one to the bottom of one without touching anything else but a wire, and I can go from the top to the top without touching anything else but a wire. So these are in parallel. So I want to know what happens to the brightness of the original bulb. And again, we can think about brightness as being the same thing as current. We'll talk more about that today. But for our purposes right now, how bright a light bulb is equal to how much current the light bulb has coming into it. So let's go think about this one, and we'll talk about this here in a second. Okay, so I think that might be about everybody. So let's go ahead and look at what we got here. So we got, okay, so a little bit of B and a little bit of A. And so I'm going to say A, which goes against what a lot of us were thinking. So anybody want to tell me what they were thinking? Either right or wrong, so we can try to, talk about this and kind of figure out where we're at. Yeah. Okay, so what I thought he said was that the voltage in both these cases, when two things are in parallel, the voltage across them is the same, and so the voltage stays the same across that light bulb. And so we know from Kirchhoff's rules, right? What is from Ohm's law, the current is equal to the voltage divided by the resistance. And so in the second case, right? So let's just imagine that, this is my favorite kind of battery, and it's like a 12-volt battery. Okay, so it's a 12-volt battery. In this case, this light bulb, the top end of it is hooked up to the top. So this is just a piece of metal. So this is 12 volts. Over here, this would be like 0 volts. So there's 12 volts across this guy. In the second case, all right, it's the same situation. There's 12 volts there. It's connected to the battery, and there's 0 volts there. And so it's still 12 volts across it. And so 12 volts, the light bulb stayed the same, so it's got the same resistance, and so the current stays the same. And so since we are talking right now on this idea that brightness is the current, they would have to be the same. Anybody else have a different way they thought about it? Or does anybody else have a question? Because the majority thought that it should decrease. So anybody want to say what they were thinking and try to understand why what they're thinking wasn't quite right? It's a pretty brave thing to do. Yeah. Does the second bulb have the same brightness? What do you guys think? So if it's an identical bulb, right? Again, it's the same situation. When we have things in parallel, the voltage across them is the same. And so if you think this is just a piece of metal, it's going to have the same voltage as the battery. So it'll have the same voltage across this, and so it'll be the exact same current for that guy too. So the same brightness for that light bulb. Okay, so yeah, so it would totally be the same. And so let's think about this. So in this case here, okay, let's just go ahead and make our resistance to be 1 ohms for the light bulb, just to make life easy. Okay, so here, the current in this case for this light bulb is 12 volts divided by 1 ohm, and so it's 12 amps. Okay, so the current going through that first one, again, we just made up numbers, is 12 amps. Now in this case here, I'm going to say the same thing. For this guy right here, okay, going through this little section, it's going to be the current over here will be 12 divided by 1. I'll just drop the units because they can't really fit. And so I get 12 amps. But I also get 12 amps over here, right? Because we got 12 volts divided by 1 ohm, and I equals that. And so what does that mean? That means the battery now is sending out a total of 24 amps, where before it was sending out a total of 12 amps. And what happens is at this junction, 12 amps goes this way, and 12 amps goes that way. Okay, so in order for that light bulb to stay the same, something had to change, and what's changing is that battery is sending out more power. Okay, it's working harder to do this. All right. Questions on this, anybody? Yeah. So does the voltage of the battery ever decrease? So the voltage of the battery, if it's not an ideal battery, can decrease. But I think for most problems, unless we state otherwise, we'll deal with ideal batteries, and so it will not ever decrease for the majority of our problems, okay? But if there's a case where we might be talking about a more realistic battery, we'll be real clear about that. Great question. Yeah. Yeah, so these are said to be identical light bulbs, okay? So they'll be the same resistance if they're identical. And again, we always neglect the resistance of the wires, again, unless we state otherwise, which we won't do very often. But the wires in general have such a small resistance compared to whatever we're dealing with, we can neglect them. So both paths should have the same resistance in this particular problem because they're identical light bulbs. Yeah, question? We're going to find that brightness is connected to voltage and to current. You can kind of do either way, so it kind of depends on which one is easier to think about, which is going to be nice, but we'll talk about that more later. Yeah, question? Sorry, can you explain again why does 24 Sure. So in this case here, right, both of the light bulbs, if you look at the voltage above and below them, right, it's going to be 12 volts. So the voltage drop across the light bulbs in both cases is 12. Right? And so that means there has to be a current in each one of 12, the way I just picked these numbers up. And that can only happen if that battery sends out a total of 24 amps. Okay? Yeah, question?
So earlier in the video that you posted last night, you stated that in parallel, current is additive. However, you
Okay, so let's be careful about this. So in this problem, the current is additive. It's 12 and 12. And so what it is, it's like the battery sending out 24. And so the current through both of those little paths is 12, and so it totally is additive. So it's 24, and it splits up into 12 and 12, right? And so what happens is when you have two things in parallel, the current through them should add up to the current that's coming into both of them, which it does. And then the voltage across them will always be the same, which it is. It's 12 volts, right? So does that make sense? Okay. Question? Well, again, so yeah, in real life, your battery, I mean, batteries sort of work harder the more current they're sending out. But in this class, for right now, we're just going to assume these are ideal batteries. So we're trying to sort of understand the basics. And then later on, we can talk more about sort of more realistic things. But in real life, a battery that's fully charged and hasn't been working too much won't really feel too much of a difference in either one of these cases. Okay, okay, and so the question is, how do you suppose outlets in your homes are wired? Do you think the outlets in your homes are wired in parallel, or are they wired in series? What's your guess? Parallel, right? If they're wired in series, every time you turned a lamp on, everything in your house would get dimmer, right? Which would be you'd be like, okay, so in parallel, what that does is basically if you turn an extra lamp on, what will happen is things will kind of dim for a second, but that's just sort of the power kind of keeping up with everything. But everything stays the same, and what it means is you're just using more current, right? So the more things you plug in, the more current that's coming out of your power source, and so you end up paying more to the power company, all right? But everything stays the same, and so everything has that. At our homes, the voltage we get is like 120 volts, and so everything you plug in gets 120 volts in a similar fashion. So the voltage drop across the resistors must be the same. And so, yeah, so a question, what's the difference between the squiggly E and the V? And again, really there is no difference for us. It's just the squiggly E is just the voltage across your battery. And so what we do is we've got this case here where the voltage drops across these are the same. And so when we try to find out our equivalent resistance for resistors in parallel, it's this equation here. Okay, so it's this 1 over R plus 1 over R style equation. And so it's important to note here that when you do this equation, okay, when you've solved this equation, okay, I don't know if you've done this enough yet, but REQ will always be less than R1, and it'll also always be less than R2. Okay? And so that hopefully goes along with, like last time we were saying that if you have more paths to go through, the resistance decreases. And that's what's happening here. When you got in parallel, you've got another path to go through. And so even though it's two resistors, there's more paths. And so the overall resistance of that place, right, like when we write equivalent resistances, we're trying to say, okay, what's the equivalent resistance of this whole thing, and replacing it by 1, it's going to be less than either one of those two things because you're giving more paths to it, okay? And so hopefully that, makes sense. So let's look here at a question like this. So this is something that will happen a lot. The book loves to kind of show pictures like this. So current flows through a light bulb. So current's going through a light bulb. If a wire is now connected across the light bulb, what happens? Okay, so now we connect a wire here, and again, wires are assumed to have resistance of essentially 0. So what do you think is going to happen to the current flow through our light bulb, in this case right here? Okay, so it looks like we got most people. Let's go ahead, give you 5 seconds. So if you didn't put an answer in, put an answer in, and we'll talk about this and discuss it. Let's see what we got. Okay, so we got a couple different answers here. So first thing, what I'd like to do is just back up to that case we just had a second ago, okay? And so let's just look at this real quick. So here's our, no, you know what, let's just go ahead through here. So I agree with C, I agree with the majority. That's good. And what we call this is we call this a short circuit, all right? And what it is you can kind of think about it, is this zero resistance is giving this path of, again, zero resistance. And so the current comes up against this light bulb, and there's this path of completely sort of freeness over there. And so it just goes right over. And so when you see this in the book or in one of my problems, okay, what that essentially does is it just bypasses the light bulb or the resistor or whatever it is it might be that's there, and all the current will flow through the wire. Okay, so this is a good question. How do electrons decide which route to take at the junction? And it's kind of like, you know, it's sort of difficult to talk about electrons, but it's kind of like that problem we had last time. We had that resistor and the wire, and the electrons kind of started making a line because it was really hard to get through. It's the same sort of idea here. Initially electrons will sort of try both paths, and what will happen is they'll get stuck going through the light bulb, and then they'll find that the ones going the other way are going to be going much, much faster. All right, and so there'll be sort of a lineup of electrons at the light bulb, and so there'll be a whole bunch of electrons there. And so, if you're a new electron, you'll come over here and say, I don't want to go there, because all those electrons lined up, and you'll go through that way there. All right, and so this is an extreme case of this. All right, but just to kind of talk about this a little bit more, what this is a case of something being in parallel, and so we can use our new parallel equation. Okay, so here's our new letters for that. And so I'm going to call the resistance of the wire to be lowercase r, and the resistance of the light bulb to be big R. And of course, we know that R is much, much less than big R. Okay, so that's sort of the information we go in with. And if I solve for this, so I get 1 over R EQ, I'll have 1 over R plus 1 over big R. And then the best way to sort of think about this and solve this is to make a common denominator. So we got to go back and do kind of some fraction business. So I'll get R over RR, and then plus little r over RR. So I get 1 over R EQ. When I add these up, I'll get R plus R over R, times R. And then finally, when I want to solve this, I'll solve R EQ, and I flip it all over, and I get R times R, R plus R. And what happens is, because I'm multiplying by this little r up here, which is, again, we're going to call 0, this whole thing becomes essentially 0. All right, and so if we think about our Ohm's law says the voltage across something is the current times the resistance. Well, over this whole piece, the total resistance is 0, so the voltage drop across this piece becomes 0. Is sort of one way to think about it. So if you want a kind of a more mathematical picture, but basically the current will go up to the top part, and so if you see this in a problem, what you basically just got to do is just ignore the light bulb in this case, and just think that and sort of replace it with a wire, okay? Questions on this? This is a tricky subject, but this is what they mean by short circuit. So sometimes in electronics, you'll have like a wire go somewhere by mistake, and it'll sort of bypass something like this light bulb that was really important, and it can cause bad things in whatever you're trying to do. And so that would be what the term short circuit comes from, aside from being a really cool 80s movie. Okay, so here's our summary then, at least so far, of stuff that we've learned to deal with resistors in parallel and series. And so parallel and series, here's our rules to deal with those. And again, these rules are similar to the capacitor ones, but opposites. You got to be super careful about that. But the thing that is similar is that the voltages across anything in parallel is always the same, and the current in things that are in series is always the same. And again, our rules for series, if I go through one and I keep going, my only choice is to go through the next one. That's sort of our definition. In parallel, if I can go from the back to the back and not touch anything else but a wire, and the front and not touch anything else but a wire, that's parallel. There'll be lots of cases where they'll try to draw pictures that look like they're parallel. You got to be careful, okay? Let's go ahead and let's give ourselves a few minutes and try this here, all right? So again, with a circuit kind of question, there'll usually be two parts. The first part will be something like this: find the equivalent resistance. So let's take just a few minutes and try to find the equivalent resistance. You probably won't get all the way there, but at least thinking about it a little bit will help. And then we'll go through and do this in a few minutes, okay? Okay, so I'm going to go ahead and call time here. So put your answer in. Again, this is a longer one. I want to make sure I can get through this example today, but I think even just starting this is a good exercise. At this point, I think that the majority had the right answer, so that's a good sign. So a lot of us are sort of have an idea of how to do this. So I do agree that it's C. So let's go through. Again, no points for getting it right. Okay, so let's do this here. So again, these are like little puzzles, and I think most people get good at this part of the problem for sure, usually. And so the first two things are you got to find something that's in series or parallel. And so here, these two guys here are in parallel. All right, and so the way I would kind of do this picture is I would replace those two guys who are in parallel with a new one. And so I'd say something like this here. So I'd say, okay, here's my circuit. So here's the 18 ohms. Here's the 10 ohms. And I want to replace this new one. So here, let me just make these actually so anybody can read them. And so the 5 and the 8 are in parallel, and so we want to use our New Deal equation with that, which is 1 over R equivalent is 1 over 5 ohms plus 1 over 8 ohms. And when I do that, okay, you can do the math yourselves. I got 3.1 ohms. So kind of a weird number. So 3.1 ohms. And so now, the next place I would go is right here. These two are in series. And this is where it gets tricky, okay? The 18 is nothing with the 10, and it's nothing with the 3.1. Like over here, the 10 was nothing with the 5 and nothing with the 8. So it's a real special thing. Next class, we're going to talk about cases where they're not in parallel in series. It's a real special thing. It makes life easier, but it doesn't always have to be. Okay, and so these two are in series, and so you can add them up. So my next step from that one would be to add those two guys up like this. And so I would end up with this 18 remains the same. And when they're in series, you just add them up. So this will be like 13.1 ohms. So here my R equivalent is 13.1 ohms. And then my last picture would be those two guys in parallel, the 18 and the 13.1. And so I would do this equation again, 1 over the 18 plus 1 over the 13.1. And when I did that, I got that final answer of 7.6 ohms. Okay? Now, again, on the video this week, I do an example of one of these, so you got another example to look through. But that's the first step. And like I said, it seemed like a good majority of us got there. If you haven't, sort of picked this up yet, it is the kind of thing that when you first see it, it can be tricky. So you might want to go back to that video and kind of watch through an example of this to get better at this. Whoop. So let's, and actually I wish I had done, here's a really nice sort of picture of this here, a sort of nice little setup of doing this here. I wish I remember I'd had this. So again, these two are parallel to the 3.1, add those up to the 13.1, these are in parallel to the 7.6, okay? And so now that's the first part. Anybody have a question on the step that I did here before we go on to what would be the second part generally with a question like this? So the second part would want to go through and ask about one of the particular resistors, like what's the voltage drop across resistor 1, or what's the current through resistor 2? And that's the part that, again, is real similar to what we did with capacitors. And so we can go through and make a nice little chart here. So here's my little chart of resistance, current, and voltage. And we start with the final step. And so this is, again, my advice is, you will probably get to the point where you can do these resistances really fast and in your head, but you want to always draw your picture so you can backtrack like this. So we start here with the simplest circuit in the world. And again, the equation we want to use is our Ohm's Law. And so I is equal to V divided by R. So here, the voltage of the 7.6, so we'll start with this 7.6 resistor. The voltage has to be the total voltage of this battery, 12. And to find the current, we just divide 12 volts by 7.6 ohms, and I get 1.6 amps, okay? Again, simplest circuit in the world, so we get the 1.6 amps. And so now I unfold this resistor into the two we just did, okay? So the 13.1 and the 18, those are the two that are in parallel. And when we unfold the resistors, one thing stays the same. And if you look back at the chart, the thing that stays the same for parallel is voltages. So I put that voltage of the 12 in there like that. And so I'll erase this to make this a little clearer. And so the 12 and the 12. And so then we take our equation to find the last piece. And so I say voltage divided by resistance. And so in the case of the 13.1, I take 12 volts divided by 13.1 ohms, and I get 0.92 amps. And in the other case, when I do that, I'm going to get 12 volts divided by 18, and that comes out to be 0.67 amps. All right? And so we were building up our chart. Now, one thing is that when you do this chart, two of these things, okay, so two of these are the same. Two of them should add up to the old one. So these two currents should add up here. Because what's happening is a current of 1.6 comes here, and it splits up into a 0.67 and a 0.92. Now, because of significant figures and stuff, sometimes these will be a little bit off, okay? But as long as they're pretty close, it's a good way to kind of go back and check where you're coming from on something like that, okay? And now we take this situation we're just at, the situation C, and we unfold that to be the 10 and the 3.1. And those are in series, right? So I write out my, right, they're in series. So I write out my resistors, the 3.1 and the 10. When you're in series, it's the current that stays the same. It's the same current. So we take the current of this one, because it's the 13.1 that I'm unfolding into these two, so 0.92, 0.92, all right? And so now I want to go through and find the voltage of the situation that I'm talking about. And so I just take my V equation like so. So V equals IR. And so say the V for the 3.1 would be a current of 0.92 amps times the resistance of 3.1 ohms. And when I do that, I get 2.85 volts. And then the V of the 10 equals IR is 0.92 amps times 10 ohms. And when I do that, I get 9.2. And so I'm just going through and filling out my chart. Again, this problem, could have said something, what is the voltage drop across the 10 ohm resistor? And so now, if that's what it asks, you're done, and you can stop, okay? And so here, again, what should happen is that these two should add up to the voltage of this guy over here. Again, because of rounding and stuff, they don't exactly, but they're pretty close, okay? So you can get a little bit tricky with rounding and stuff like that. And so finally, our last step, we take that 3.1 and we unfold it to the 5 and the 8. And so it's the same sort of idea. And so the thing that stays the same here is going to be, so this is parallel, so it's the same voltage. So we take that same voltage of 2.85, and so for our last step, we're just going to do our I equals V divided by R. And so I'll just do one of those because I think you're getting kind of used to this. So 2.85 volts divided by resistance of 5. And when I do that, I get a current of 0.57 amps. When I do the same for the other one, I get a current of 0.36. And so now I've found the voltage and the current in all the different parts of the circuit, which basically means you know everything about the circuit. If the circuit was a bunch of light bulbs, you could then go through and figure out what the brightness was, this kind of a thing. So you basically have done everything you can for this particular circuit. And so I think what I'd like to do is just real quick, is just, well actually, was there questions on anything we did on that one, guys? Just real quick before we go, I just want to formalize how the energy in the circuit works. And so here is our equations. So you'll be asked, again, these questions about brightness. And brightness is basically the power used by your resistor. And so here's 3 different equations to figure out the power dissipated by a resistor. And so one is I squared times R, and one is V squared over R. And so basically, if you can relate the voltage or the current of 2 resistors that are the same, you can tell which one is brighter using this equation. So there's a question tomorrow on your discussion sheet about that. Okay, we'll pick this up next time. Thanks, guys. I'll be down here if you have any questions.